Hi, everyone. Can you hear me? Sounds good. Okay. I'd like to thank the organizers for the opportunity to be here today and to talk about, I'm going to talk about JWST observations of disks, for which I think that there is a revolution ongoing. I myself was a postdoc at NORLab many years ago working with Joe Najita, so it's always a pleasure to be back here in Tucson. And since that time, I've been working on JWST, which is why I'm so enthusiastic about it and eager to tell you about it. So this slide sort of illustrates the gains that have been made by ALMA on the observation of disks, going from the left-hand side. Geez, is it the top button? Oh, it's this one. Pre-ALMA to post-ALMA. And this is pre-JWST for a debris disk and then post-JWST for a debris disk. Let's see. So in the canonical picture of star formation, star and planet formation, we all think of stars forming from the interstellar medium in clouds of dust and gas. There may be density knots that have a little bit of angular momentum so that as they collapse, they naturally support a disk around them. During the early phases, this disk is enshrouded in its natal envelope of gas and dust. And then over time, the envelope clears to reveal a protoplanetary disk. And in this case, the solid material in disk may accrete to form larger objects like planetesimals or planets. And you can see planet formation in these protoplanetary disks. And eventually the gas will dissipate as well. It'll accrete onto the star and to planets. And so so I'm going to really focus on the debris disk phase here, but I will also show some really beautiful data from protoplanetary disks to give you a feeling for the capabilities of JWST. So as I mentioned, ALMA has really improved our picture of the evolution of disks through very high angular resolution observations that are very sensitive, that also give us a detailed picture of the chemistry. And really it was, I think, a revelation when the image of HL tau was first taken and all of the detailed ring structure was seen in the disk. And it triggered a whole conversation about what causes the ring structure. Is it planets in the disk? Is it chemistry? Things like that. And then this is sort of an ALMA picture of Fomalhaut, which is a very famous debris disk. And in this particular case, what you're seeing are less large dust grains that are created by collisions among planetesimals. And essentially, by looking at the spatial distribution of the dust, you can look for signatures like warps and asymmetries that can tell you something about the interaction between the planetesimals and planets. And so I think the ALMA disk revolution has come. There are so many really wonderful large programs exploring protoplanetary disks. And there are going to be 2 talks in this session about these ALMA observations. So Ding Chen is going to tell us about CO isotopologues, and Ilaria is going to give us a little broader perspective. But I'm going to argue that JWST will have the power to also create a revolution in our understanding of disks. And these are some early observations that were made of both protoplanetary disks and also debris disks. This is a simulated image of PDS-70 in which you can see the planets that are forming. This is data that was taken with nearest AMI. And then over here, this is a picture of Beta Pic that was seen in the mid-infrared with MIRI. So we start to see planet formation in protoplanetary disks, and we see planets in these debris disks. I'm not going to talk at all about another family, a really interesting family of work, which is the dynamical interaction between planets and planetesimals in the debris disks. I'm going to focus more on composition and chemistry for both protoplanetary and debris disks, like understanding how planets and planetesimals inherit their materials from the disk. But I did want to give a shout out to, there's a couple of talks that are in this area of understanding the dynamical interactions between planets and disks. One is an observational talk by Katie on the very exciting new observations of TWA7, where JWST has discovered a Saturn mass planet, and Katie's going to show us some NIRCam observations that show the disk as well. And then Antranik is going to go beyond massless models and imagine what happens when planetesimals have mass. So that was my quick introduction. And so now I'm going to try and get into observations of protoplanetary and debris disks with JWST. So going back to that beautiful image of HL Tau, when that image was first sort of discovered, it wasn't understood whether or not the different ring structure was created by planets in the disk, that there could be many, many planets, or whether or not, for example, sublimation fronts were important. So when we think about protoplanetary disks, we expect there to be many volatile species, and these condense out at different radii in the disk. The sublimation front that we're all most familiar with is for water ice at about 100K. So interior to about a few AU in our solar system, it's too warm for water to be in the solid phase, so it's in the vapor phase. And then exterior to that location, water can condense into solids. So we think this was very important for the formation of the planets in our solar system because water ice increased the surface density in solids by about a factor of 2, and we think that enabled core accretion, so the ability of Jupiter and Saturn to rapidly form cores before creating gaseous envelopes. But when you look at the chemistry in disks, we see not only water, but also, for example, other volatile species like carbon dioxide, carbon monoxide. And the sublimation fronts for these materials are expected to be at different locations further out in the disk. And so when you go into larger distances, not only does water ice condense, but now carbon dioxide condenses, and in the very cold outermost regions, you can have CO condensation as well. On the right-hand side, there's sort of a similar sort of picture for refractory materials where silicate grains, remain in the solid phase until you get very close to the star. They sublimate at temperatures of 1500 Kelvin. And there's also a soot line for carbon. I would say that JWST for protoplanetary disks has been absolutely amazing. And we are really getting to the point where there will be this power in statistics of observing hundreds of protoplanetary disks and understanding the chemistry, the disk chemistry going in the inner disk. So this is just an example observation. This happens to be DF Tau obtained by Sierra Grant from the MIRI GTO team, showing the mid-infrared spectrum from 5 to 25 microns. And what the great advance from JWST is the increase in spectral resolution, enabling sort of the detailed characterization of these forests of lines. Particularly in this case, you can see a forest of water emission lines. And not only that, but the detection of other molecules as well, such as CO, C2H2, HCN, CO2. So this is a far cry from the days when we were working on Spitzer data with a spectral resolution of about 500 instead of 3000, in which you were only really able to see the continuum and maybe the silicate features. And then Joan and John Carr pioneered very high, very sensitive high SNR spectra to try to find these water emission lines, which they did, and now JWST just really beautifully characterizes them. As I mentioned, there are observations of hundreds of targets now, and I just pulled out a couple of examples just to give you a flavor for the things that people are learning. This happens to be a study that was done very early on in the mission by Andrea Bonzatti, looking at Titari stars, both a couple of compact disks as seen by ALMA, with GK Tau as an example here, and CI Tau as an extended disk here. And you can see their MIRI spectra And you can see it's a little bit hard to see by eye here, but there are differences in the excitation of the water here. So the hypothesis for these compact disks was essentially that they have experienced or are experiencing pebble accretion. So the accretion of icy pebbles from the outer part of the disk. And that's the reason why they appear compact. And so the mirror data really beautifully can measure the water vapor and its excitation. And in this particular study, they find that these compact disks have an excess of cool water emission, 170 to 400 Kelvin, which is around the expected sublimation front for water ice, with an equivalent emitting radius of 1 to 10 AU. So this could be created by pebble accretion. Another, I think, really interesting result has been looking at the chemistry as a function of the host star's mass. And this is work done by Sierra Grant. This is the GTO Mines team, where they've noticed that there is a systematic difference between the spectra of T-Tauri stars and very low mass stars and brown dwarfs. The T-Tauri stars, as I mentioned before, they're rich in oxygen-bearing molecules, including water. But as you go to things that are much lower in mass, below 0.2 solar masses or so, you have a change in the chemistry from being oxygen dominated to carbon dominated. And so you can see that the forest of water emission lines has disappeared, and there are many carbon species here. And so they detail very nicely that there's an anti-correlation between the ratio of the line fluxes of acetylene in water and stellar luminosity. And they see not only this correlation or anti-correlation with luminosity, but they see that there are other quantities that are also related as well, like the strength of the silicate feature, the stellar accretion rate, and the disk mass. As you move out to larger distances, we study these in reflected light now using NIRSpec IFU. This is data from Ilaria Pascucci's really beautiful program. And you can see the thing that I'm most excited about in the reflected light observations is access to the volatile ice features. So you can see there's a 3-micron broadwater ice feature, which has been very hard to characterize from the ground because of the atmosphere. Also the 4.2 micron feature for CO2, and the CO feature around 4.6 microns as well. But the power of these IFUs is not only the ability to take these really beautiful spectra, but in some cases also to image in individual lines. And so you can see here that each one of these is, this is a color composite, and it's broken down into, for example, iron emission from the jets, H2 emission from the outflow, CO emission in the continuum. And so you can really kind of dissect the disk in looking at it. And so Nauman is going to give us a very nice talk focusing on the jets and winds from these observations. So to move on to debris disks, because that's my favorite topic, this is the typical planetary system architecture that we think of in our solar system and that we envision in other planetary systems as well. The key features here are, so you have the star, and then there are planets in orbit around the star. And there's a gradient in the temperature of the circumstellar matter as you go away, just like in the protoplanetary disk. And so things, if you want to study the inner parts of the disk, you can study, for example, the thermal emission from the dust. One of the things that we've learned from early JWST observations is that these debris disks are quite active. For example, this is a result from my GTO program observations of Beta Pic, showing how the spectrum of this object has changed over 20 years between the initial Spitzer observation in 2004 to 5, that's the blue one, compared with the JWST MIRI observations in 2023. And you can see it's really shocking. The silicate emission features, the 18 and 23 micron silicate emission features that were seen more than 20 years ago have disappeared. And there's a loss in the continuum as well here that tells us about an asteroid's mass of material has gone missing. And so the model for this is basically there was a giant collision just prior to the just prior to the Spitzer observations. And when the collision occurred, it created a lot of little tiny dust grains, and radiation pressure subsequently blew those dust grains out of the system so that they're not detected anymore. We've had other serendipitous discoveries as well. This is also for Beta Pic, the same data set. My graduate student, Caden Worthen, discovered argon-2 emission at 7 microns in this system. This is a spectral differential imaging image in which he took a slice of the data cube in the argon-2 line and then one just adjacent to it and differenced them. And so you can see where the argon-2 is rising. It's mostly centrally concentrated, but it is extended. And for comparison, he's shown here this is a continuum PSF subtracted image with the argon-2 contours overlaid. And you can see the planet here and that the argon reaches at least to the distance of the planet, if not beyond. So we're learning unexpected things about oh no, this didn't come out right. The detailed chemistry of the disk. What I wanted to show you here was that these observations are now being interpreted. There's a lovely paper by Yanqing Wu trying to understand, disentangle the abundance of the different atoms compared to their excitation. And she's able to show that these results indicate there's an enhancement of argon in this particular disk, which suggests that the gas is created by the destruction of icy planetesimals. One of the other really interesting results from ALMA has been the discovery of CO in debris disks. So this particular plot shows CO mass as a function of age with the approximately 24 systems that have been discovered populating this particular plot. What has been really striking has been for about half of them, the disks are very, very massive. So it's strange because the disks appear to have low dust masses that are consistent with debris disks, this later stage of evolution, but then they have gas masses that are very high and more consistent with protoplanetary disks. So the question kind of is, what is the origin of the gas in these systems? Is it is there some sort of evolution happening in the protoplanetary disk where there's a loss of small grains that leads to this high CO mass, or is it that they're genuinely gas that's created from collisions of planetesimals that's secondary? So Sorsha is going to give us a nice talk about observations, ALMA observations of CO in debris disks. There is a large program called ARCS that was approved. They just submitted a raft of papers to the journal, which hopefully will be published soon. And Sorsha's talk is going to concentrate on the spatial distribution of CO in the disks. So JWST has been able to provide diagnostics into the CO in disks. For us, this was a little bit surprising for debris disks, but I think in retrospect, it's something that perhaps we should have expected. So I'm highlighting here a research result from Cicero Liu. These are NIRSPEC observations of a star called HD 18132. 131488, which you can see here. This is the spectrum. And when it was originally taken, it was really striking that you see this forest of CO emission lines. This star happens to be relatively early spectral type A1, which means that it produces a lot of ultraviolet radiation. And so what we think that's happening here is that the CO gas on the surface of the disk is absorbing the ultraviolet light, and it's pumping the CO from the ground state all the way up into an excited electronic state. And then from there, it cascades down. So the emission is a non-thermal, it's fluorescent. And so the vibrational temperatures can be very hot, but the rotational temperatures are actually quite cool. What's really exciting is that this gives us a way to probe gas that can be close in the inner part of the disk. Cicero believes that the gas here is within the inner 10 AU. And the other thing that's super exciting is that it gives the possibility of probing very low masses of CO, much lower than we can do with ALMA. So this is a plot that Cicero's made showing CO gas mass. Now for, again, these debris disks, but now they're ranked by distance or spectral type. And so these are all ALMA observations, and the one here shows you the ALMA CO measurement for this particular star, HD 181, or sorry, 131488. And the star down here, which is several orders of magnitude lower, is the mass of gas that Cicero is able to detect in these UV fluorescent observations. So it's really, I think, enticing, the possibility of being able to detect trace amounts of CO gas in a way that's more sensitive than ALMA. So in addition to the gas, for debris disks, we've been learning a lot about the composition of the outer disk. And we think of the debris disks as being sort of extrasolar analogs to the Kuiper belt in our own solar system. And so there is a large program on TNOs that showed that there are three classes, one that's water ice rich, another that's CO2 ice rich, and then another that's organics rich. And the reason why they have different compositions is probably because they formed at different distances relative to the snow lines. So this is now data from my GeoCycle 1 program that's been analyzed by Chen. This is HD 181327, but this is a reflectance spectroscopy. This is taken with NIRSpec IFU, and then he's extracted spectra at various distances. And so there's this discovery of the broad 3-micron water ice feature, including the 3.1 micron Fresnel peak that indicates crystalline water ice. For us, what was really striking is the similarity between the 181327 spectrum and the water ice rich KBOs, sort of underlining the connection between debris disk planetesimal belts and also the solar system TNOs. This has now been done also for beta PIC, where we see not only water ice, but also CO2 frost and fluorescent CO emission. Excitingly, this is work done by Sarah Betty, who's a postdoc at ST. And excitingly, with the detection of the 12 and 13 CO2, she can measure the abundance of CO2 relative to water, and thinks that she finds about 10%, which is commensurate with that found in comets. This is really interesting, I think, because Beta PIC is a much more massive sun or star than our sun. And so it indicates that there's this possibility that the mechanisms by which comets and TNOs form in our solar system is active in exoplanetary systems in general. So the very last thing I want to talk about is a recently approved far infrared project. This is a pioneer mission called POEM. This is a balloon-borne experiment to do far infrared spectroscopy led by Gordon Stacy. It's a 1.8 meter telescope at 45 kilometers above Antarctica, and it has two sort of key instrument parts. One is a VIPA that enables high spectral resolution R of 100,000 spectroscopy. And the other is MKIDs that enable observations at 35 to 112 microns. It's expected to launch in December 2029. So why you should care is because these observations will become public about a year after they're made. And they will address many of the questions that I've sort of sketched out in this presentation today. So for protoplanetary disks, there will be observations of 30 to 50 disks to understand the mass in the bulk gas mass through observations of HD. There'll be observations of water ice and water vapor. These are going to be, this is a wavelength range in between JWST and ALMA, so it'll be cooler water than JWST. And then also looking at oxygen 1 to understand the energy balance. For debris disks, again, looking at solid state ice features, at the difference between amorphous and crystalline water ice and understanding the processing of water ice and disks, understanding the origin of gas and debris disks through the observation of O1. And then there will be some observations of solar system objects as well. So Neptune, looking at HD to measure the D to H ratio, and then also water abundance in the upper atmosphere. And I just wanted to give a last shout out to another presentation in this session by Brenda Matthews, who's going to talk about more far infrared instrumentation, I think, including PRIMA. So with that, I'm just going to put up my summary slide, which is that I'm super excited for JWST. I think it's making great contributions to our understanding of disks. And I hope that, in 10 years or however many few years time, there will be the same sort of JWST disk revolution as I think has happened out the longer wavelength side using ALMA. So thanks for your time and attention.
Thanks, Christine, for that great talk. And perfect with timing. The next speaker, Sorsha, can you come up? Well, we can help you set up. And in the meantime, we'll take any question for Christine. Yes, Emily.
Yeah, thank you. There is an online question, which I'm going to read out. The question is from Brenda Matthews. Thanks. Yeah, thank you. So the question is from Brenda Matthews. The fluorescence of CO to detected lower masses must be limited to stars producing enough UV radiation. What is the latest spectral type at which you would expect this to be an effective technique?
Yeah, that's a really great point that you need ultraviolet radiation in order to create fluorescence because you have to do the pumping in the ultraviolet. And so empirically, and also based on modeling, we think that it's really early A-type stars that are best suited for fluorescent emission. So I did show in the beta-pic spectroscopy, you can see there's little tiny row vibrational lines at 4.6, 4.7 microns, and that's about an A5, A6 star. So that's about where it starts to peter out.
We have a question on this side of the room.
Thank you so much. Thanks, Christine. I was really interested to hear that it's possible that the CO ratios or those ices to water ice is like our solar system. So have you thought about whether the thermal history makes sense? Because beta-pic is obviously much younger, whereas comets in our solar system have had, 4 billion years to be irradiated and those kind of volatile sublimated. So have you thought about that? Does that make sense that beta-pic in the solar system?
Yeah, no, thanks, Jay. Those are really interesting questions. And I think it highlights that there's a lot about even solar system ices that we don't understand and we're just starting to learn now. There have been hypotheses that, for example, all of the ice in the solar system should have originally formed as amorphous water ice, and it's only through processing that you get crystalline water ice. Yet it's really fascinating when you look at all the objects in the solar system, they all have crystalline water ice. And I don't think it's entirely understood why that is. So there's been, for example, a hypothesis that the reason why objects in the cold classical belt might have crystalline water ice is because they were stirred during a planet migration. So as Jupiter and Saturn moved out, they interacted with the planetesimals and induced a larger velocity dispersion among the planetesimals so that they collided with bigger relative velocities. So if the relative velocities at which they collide is 4 kilometers or more, you actually get a phase transition in the collision going from amorphous to crystalline water ice. But I guess this is, for me, one of the things that I'm really interested in is what is the history of the processing of the water ice? It's really interesting in these two that we have, beta-pic has amorphous water ice, and yet 181327 has crystalline water ice. They're the same age, they're similar in spectral type. And so, another possibility for amorphous water ice is that you could have cycling of water ice of water in the system, where basically the ice comes close to the star, it sublimates, and it cycles outward, and then it condenses in the outer disk where it's very cold, and then it would condense into amorphous water ice. But this is a sort of thing where I feel like we need more data because we only have these two objects to try to understand and to connect to the solar system. Yeah.
Okay. Maybe we'll take one last question.
Hi, Zachary Hartman, NASA Ames. So some of the disks that you showed were in systems that were binaries. Did you see any differences in the chemistry of the disks in binaries versus non-binaries?
Yeah, that's a question that I'm not equipped to answer for protoplanetary disks. I don't know if Ilaria would want to take a stab at it.
So this is a very good question. I know that there were proposals, JWST proposals to investigate this. I don't think they went through. And at the moment, I don't recall that there is any significant difference, but that's because the sample is too small.
Thanks, Gloria. Thanks, Christine, and all the great questions. Okay, in the interest of time, we will move on to our next speaker. So next up,